So we're going to learn a little bit about physics in this chapter. We need to talk about light. So light is a form of electromagnetic radiation. It's composed of perpendicular oscillating waves. There's an electric field and a magnetic field. Electric field is a region in which an electrically charged particle experiences a force. A magnetic field is a region where a magnetized particle experiences a force. Now we have more experience with magnetic fields. You've got a magnet, like the cap on my Apple Pencil has a magnet in it, right? And so the cap just snaps right on there. You go to put up a note on the refrigerator. The magnet sticks to the refrigerator because of the magnetic field. Electric fields are similar, but they work with charged particles. So electromagnetic radiation moves through space, all forms of it, at the same speed. We call it the speed of light because it's the speed at which light moves. Okay? And that speed is 3 times 10 to the 8th meters per second. It's really fast. Okay? So I'm just going to warn you, in experiment 7, there's a question that a lot of people get wrong because it's having you order some different colors of light according to increasing wavelength or frequency or energy, and then it says order them by speed. And students do all sorts of crazy things. Which moves faster, red light or green light? They both move the same, the speed of light, right? It's all the same. So there. So here we have an illustration of these two oscillating fields. So here's the electric field oscillating up and down, the magnetic field oscillating in and out. They are traveling together in the same direction, and they're traveling at the speed of light. We know from real life experience that sound does not travel as fast as light, right? If you've ever been to a really big stadium and you watch the person down there saying something, the sound you get compared to what you see their mouth doing, it doesn't seem synchronized because there's a delay. And it's not much of a delay, but we still perceive it. But an even better illustration is thunder and lightning. So here we see lightning striking. It looks like it's striking a building here. We know from experience that you see the lightning strike, and then you hear the crack of thunder. Because the light comes to you at 3 times 10 to the 8th meters per second, the sound of the thunder comes at 340 meters per second. Much, much slower. And that's why you can estimate how far a storm is from you by counting the number of seconds between when you see the lightning and when you hear the thunder, because that gives you an idea of the distance. So light is a wave, and waves have characteristics. The amplitude is how tall the wave is. And so these are sine waves. They're going up and down across basically a zero here. So if you think of this as zero, they're going up and then they're coming down. So positive, negative, positive, negative. Amplitude is the distance from a node where it passes zero to a crest, or from the node to a trough. It's going to be the same. Amplitude measures the intensity of the light, how bright it is. So a larger intensity is going to be a brighter light. We can also measure the wavelength, the length of the wave. That's from one peak to another, one crest to another. That's given the symbol lambda, which looks like an upside down lowercase y. So here we have illustrations of 3 different waves. They have different wavelengths. So here's this wavelength, and this one's smaller, and this one's smaller yet. The wavelength changes the color of the visible light. Our eyes perceive different wavelengths as different colors. The amplitude, how tall those waves are, is the intensity of the light. So a dim light or a bright light, these would have the same color because their wavelength is the same. Their speed is the same. but the intensity it's taller, it's more intense. We can also talk about the frequency. The frequency has the symbol nu, which looks unfortunately like a lowercase v. Frequency is the number of waves that pass a given point in a period of time. So it's the number of waves in a given amount of time, or the number of cycles in a given amount of time, and a common unit is the hertz, which is a cycle per second. So 1 hertz is 1 cycle per second. The total energy of the waves is related to the amplitude and the frequency. The larger the amplitude, the more force it has. The more frequently the waves strike, the more force there is. So we can think about a person at the beach, right? You go to the coast. And so if we have, well, let's not start there. Let's start. If the ocean is pretty calm and the waves are coming in and they're not very big, you can stand there in the surf and the waves crash over you and you feel them hitting your legs, but it's no big deal, right? If the waves now are much taller, are you going to experience a different sensation when those waves hit you? Yeah, if this wave that's as tall as you are, higher in amplitude, hits you, it's probably going to knock you over, right? It has more force, it has more energy. Higher amplitude means more force, more energy. We can also talk about the frequency. So here we've got these nice gentle waves, they're coming in. All of these forms of light move at the same speed. But if the wavelength is shorter, you're going to get pounded by those waves more frequently, right? The frequency is greater. And even if they're not very big, just so many of them coming at you so quickly is going to be a lot more force than the ones that are just coming, 1 every minute or something. Now I've got 10 per minute, right? It's bang, bang, bang on you. Any questions? Yes?
So with the hertz, when it says cycles per second, does that mean like the wavelength per second?
Yeah.
Is that the same thing?
Yeah, so the hertz would be how many crests per second, or how many troughs per second.
Gotcha.
So how many cycles, which would be from one point all the way through the cycle to the next cycle. Yep, good question. Anybody else have any questions? So all of these forms of light travel at the same speed. So if they're all traveling at the same speed, a shorter wavelength means a higher frequency. So the wavelength and the frequency are inversely proportional. And they are related by this, I don't know where that came from, by this equation. The frequency equals the speed of light divided by the wavelength. So again, we can look at the waves here. If these waves are traveling at the same speed, this one is going to hit less frequently than that one, right? Higher frequency, shorter wavelength. The color of the light is determined by the wavelength, which is related to the frequency. They're related to each other, so you can say they're different frequencies or different wavelengths. Yes, they're both. White light is a mixture of all the colors of visible light. It's a spectrum. If we run white light through a prism, as the light goes through the surface between air and the glass, the different wavelengths are bent differently. And then it comes to this surface and it gets bent again, and we get the white light being separated into a rainbow. And this is exactly how the rainbows that we observe in the sky, or the ones in the lawn when the sprinklers are going, or the ones from the chandelier making little rainbows all over the dining room, it's all the same idea. White light is composed of these colors: red, orange, yellow, green, blue, indigo, and violet. Now, I've never been really clear on what exactly indigo is, but it's between blue and violet. A good way to remember that order, Roy G. Biv, like somebody's weird name. Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. We see this woman is wearing a red shirt. So white light hits her shirt absorbs many of the wavelengths, but it does not absorb the light with the red light. And so the red light is reflected and comes to our eyes, and so we perceive her shirt as being red. This is a part of physics that's really interesting. Let's do this example here. A laser dazzles the audience in a rock concert by emitting green light with a wavelength of 515 nanometers. Calculate the frequency of the light. Like, oh man, that looked like it was going to be a fun problem. A rock concert and a laser and, shoot. Yeah. Well, we've got a wavelength. So wavelength is lambda, 515 nanometers. It says calculate the frequency. Well, we've got that equation. Frequency is equal to c, the speed of light, divided by lambda. C equals 3.00 times 10 to the 8th meters per second. You don't have to memorize that. If you need it on an exam, I'll give it to you. So we can just use this equation without rearranging it. The speed of light, 3.00 times 10 to the 8th meters over seconds, divided by 515 nanometers. Are the units going to work out nicely? No. Meters and nanometers won't cancel out. We want to end up with frequency, which would be per second. So 1/second is the unit we want to end up with. So you could take this and convert it into meters, or we can just use our knowledge of what nano means. Nano means times 10 to the 9, right? So instead of writing nano, I'm just going to write what it means. Nano means times 10 to the 9 and meters. That is not in proper scientific notation, but that's okay. The calculator still understands it. So 3 times 10 to the 8th divided by 515 times 10 to the, it's not 10 to the 9, it's 10 to the minus 9. Yeah, 10 to the minus 9. I'm getting 5.83 times 10 to the 14. And that would be, we could write that as 1/second, we could write that as second to the minus 1, or we could write that as hertz. Those all mean the same thing. The frequency of the light, 5.83 times 10 to the 14th hertz. Questions?